Hello, welcome to Simon Solutions. In this video, we will discuss JAM 2020 question paper, question number 21 to 30. Okay, let's start. So this is the question number 21. The complex which does not obey 18 electron rules. That's okay. So how can we calculate the 18 electron rule? So to calculate the 18 electron rule, we know this is cobalt. The electronic configuration is 2d7. So total 9 electrons. Okay, 2 cobalt here, 9 into 2 plus each CO provides 2 electrons. So 8 into 2. So total number of electrons is 18 plus 16 equal to 34. And we know there is a 2 cobalt here. So there is a CO bond. Cobalt metal bond present that provides 2 electrons. So total 36 electrons. So it follows 18 electron rule. So it follows 18 electron rule. In this case, iron provides electronic configuration is S2d6. So 8 electrons plus CO provides 2 into 4. It's equal to 8 plus this 2 electron plus 2. So it's also follows 18 electron rule. Option C, in this case, each hydrogen provides 1 electron. Mn d5 plus S2 7 electron plus 7 CO2 into 5. So it also follows 18 electron. Option D, in this case, you can see eta 5 C5H5 means 5 electron provider 5 electron plus ruthenium is from the family of iron. So it also provides 8 electrons. Chlorine 1 electron plus CO2 electron. Okay, here in this case, you can see it's PPH2. So any group from nitrogen. Okay, nitrogen, if it satisfies 3 valency, suppose NH3 like this, okay, or NR3, okay. So this is a 2 electron donor. So if it's 3 valency, it will be a 2 electron donor. Okay, but in this particular question, you can see it's only 2 valency satisfied system. PPH2 is the molecule given. This is the molecule given. If the 2 valency is satisfied, so it will be like this. If 2 valency is satisfied, then it is a 1 electron donor. So plus 1. So 13, 5 plus 8, 13, 14, 15, 16, and 17. So only a 17 electron species. So it does not follow 18 electron rule. So this is the answer. Option D is the answer for question number 21. Now let's see what is the question for the answer for 22. This solves the structure of HFEs. It's a direct question. In the case of HF, we know there is hydrogen bonding, but the shape of the HF molecule is like this. It is option B is the correct answer. It is the shape of the molecule. It forms in this format. Okay, so that is the answer for option question number 22. Question number 23. The number of DD transition expected for the complex CuNH3 twice, H2O 4 times 2 plus. This is the question given. So how can we answer this question? This is question is asked for number of DD transition. To find the number of DD transition, we should follow the orbital diagram. Okay. So here it is a Cu2 plus system, So it follows D9. Okay. The orbital diagram for D9 system will be like this. Term is D. So orbital diagram will be like this. Okay. T2G, EG, T2G. Okay. This is the orbital diagram for the right side of this orbital diagram represents D1, D6 system, and left side represents D4, D9 octahedral system. Okay, D4, D9 octahedral system represents the left side of the orbital diagram. Okay, so we expect for D9 system, we expect one peak corresponds to EG2 T2G excitation for D9 system. But in this particular question, you can see the question is given like this. This orbital diagram we studied for octahedral system. Okay, octahedral system. But in this particular case, you can see the ligands are not same. Okay, 4 ligands of water and 2 ligands are NH3. So the symmetry is lost here. It is not a pure octahedral system. The point group will be D4H. So this type of system, the orbital diagram will have some changes. So let's see how we should approach this type of problems. For this type of molecules, what happened is the upper state, T2G state, will be splitting into splitting into 3. Okay, so we'll get the excitation will be like this: 1, 2, 3. So corresponds to these 3 excitation, we will get 3 peaks. Okay, why 3 peaks? It is because it is not a pure octahedral system. 2 ligands are replaced, 2 NH3 is replaced, 2 water molecules replaced by 2 NH3. So for this particular type of molecules, the answer is option C. This is the question number 24. The plot showing the magnetic behavior of oxy and deoxyhemoglobin. Oxyhemoglobin is solid line and deoxyhemoglobin is dashed line. To solve this particular question, we should know 2 basic things. We should know the magnetic behavior of oxy and deoxyhemoglobin. That is the first thing. And second thing, we should know the relation between temperature and the magnetic property of diamagnetic and paramagnetic substance. Okay, so we will discuss that. First of all, we will discuss the magnetic property of oxy and deoxyhemoglobin. Okay, oxyhemoglobin and deoxyhemoglobin. For deoxyhemoglobin, it's a high spin D6 system. Okay, high spin D6, high spin. That is the characteristic of deoxyhemoglobin. For D6 means 6 electrons will be like this is the electronic configuration of deoxyhemoglobin. So it will be paramagnetic. Oxyhemoglobin, it's a low spin D6 system. D6 low spin system. So the electronic configuration will be like this. So it's a diamagnetic system. Okay, this is the basic thing you should know about oxy and deoxyhemoglobin. Now, second thing, you should know what is the relation between temperature and magnetic property. Okay, so if you plot the temperature in the x-axis and magnetic property in the y-axis, the paramagnetic substances, okay, the magnetic property of the paramagnetic substance will change with temperature. Okay, for paramagnetic substances, chi m is inversely proportional to temperature. Okay, if temperature increases, the magnetic property of the paramagnetic substances decreases. So we should expect a peak like this. Okay, but for diamagnetic substances, the temperature will not affect the magnetic property, so it will be a straight line. So we should expect a graph like this. For diamagnetic substances, it will be a constant. It will not change with temperature, but for paramagnetic substances, it will change with temperature. So we should expect a peak like this. But you can see in the options given, If that is the concept, we will go for the option C. But there's a problem here. You can see it is not the chi-m that is given on the y-axis. Here in the options, it is not chi-m. It is chi-m into T that is given in the y-axis. Okay. If chi-m into T is given in the y-axis, then our plot will be like this. Temperature will be, if chi-m into T is in the y-axis, then it will be a straight line. Okay. So both the paramagnetic and diamagnetic behavior will give you a straight line. So it will be option 1, option A or B. From option A or B, you can conclude the options by looking at the value of. You can you know that the paramagnetic behavior, the magnetic susceptibility of paramagnetic behavior, paramagnetic substance is very high when compared to diamagnetic substances. So the option A will be the right answer because it will have, you can see the value of the chi-m will be very high for paramagnetic substances. So the answer is option A. Now, question number 25. So the major product formed in the following reaction is, this is the question. So to solve this question, this is a question from organic chemistry. So when you do the questions in organic chemistry, you should approach the question like this, because in organic chemistry, you should identify the reaction. That is the first thing you should do. So when you learn a particular organic reaction, you should learn how can we identify this particular reaction in the question paper. Okay, so you can see it here. This is a ketone, and this ketone have alpha hydrogen. So let's see. Let's approach this problem like this. It's a alpha haloketone. If alpha haloketone is given in presence of a base, it will be Swarovski rearrangement. Okay, that is how you should approach the problem. Okay, alpha haloketone in presence of a base. Okay, so the problem is like this. MEPH okay, so here we have alpha hydrogen here. Okay, so the base will remove NaOMe will remove this proton. Okay, so carbon will be generated at the alpha position. So this is the mechanism of our Swarovski rearrangement, MEPH. Okay, next step, it will attack here cyclopropane ring formation. Now OMe minus will attack the carbonyl group. It will act as nucleophile in the second step. So you will get the product like this. In the second step, when it comes back, it will cleave like this. Okay. Minus charge will be here. Double bond OMe. Okay. We are here, and it comes back. This will remove. So we will get OMe, MEPH. This is the answer. So this is known as Swarovski rearrangement. Option A. Option A is the right answer. Okay. Now question number 26. The rate of solvency for 1 to 4 follows. So in this particular reaction, this is very important because normally in every question paper you can see this type of questions. The rate of solvency means the rate of SN solvency means SN1 mechanism. Okay. So if a question like this asks, how can we approach the problem? So this question is about the SN1 mechanism. So if a question like this comes, you should approach the problem like this. You should arrange the molecules in the increasing order of the stability of carbocation. Okay, if stability of carbocation increases, then rate of sololysis will be increased. Okay, the rate of sololysis is directly proportional to rate of stability of carbocation. That is the idea. You should approach the problem like this. Okay, so after the removal of bromine from each species, after the removal of bromine, so first compound will be like this. Okay, so carbocation will be formed like this. First carbocation will be like this. Second carbocation will be like this. Second molecule will be like this. Third carbocation will be like this. And fourth carbocation will be like this. So you should compare the stability of carbocation in each species like this. Okay, if you look at the first option, you can see the carbocation is forming at the bridge center. Okay, so carbocation at the bridge center is least stable. It's not a stable system. It's not a stable system. Okay, bridges and carbocation at the bridge center is not a stable system. Here you can see the second option. You can see this carbocation is a tertiary carbocation and it has resonance stabilization. So this is a stable system. Okay, so we should compare the stability of each species. So you can, if you compare 1 and 2, definitely you can see, you can say 2 is more stable than 1. What about the third one? Third one, you can see this carbocation is an aromatic system. Okay, this is an aromatic system. There is only 2 pi electrons and it follows the all the conditions for an aromatic system. It's a 2 pi system. It is conjugated and it's a cyclic system. So it's a aromatic system. What about the fourth system? It's a 4 pi electron system. It's a anti-aromatic system. Anti-aromatic. Okay, so the fourth one is anti-aromatic. Anti-aromatic system is highly unstable. So if you compare the stability, it will be like this. 3 is most stable, then comes 2, then comes 1, then comes 4. This will be the order. So the answer is option C. This is question number 27. Most stable species in each pair of conformations are. Okay. So if we compare the first 2 pairs, the idea is if you have cyclohexane systems and the cyclohexane system has bulky groups, the bulky group at the equatorial position is the most stable system. Okay, bulky group, that is the idea. Bulky group at equatorial, that is a stable situation. So definitely you can see the bulky group is at the equatorial position is in the first case. So first one is the stable one. Compare the third and fourth compounds. Here in this cyclohexane system, in the ring there is a heteroatom and heteroatom have lone pair of electrons. If such systems are comes, then you should think like this. If this is the situation, then the bulky group at the axial position is the most stable situation. If you have heteroatom in the ring, the bulky group at the axial position is the stable system. So fourth one is the stable situation. Now we compare fifth and sixth one. You can see it here. In this case, we have OH here at the substitution position. Okay, so if OH comes and we have a oxygen or heteroatom present in the ring, there is a chance of hydrogen bonding. Okay, if oxygen or fluorine present, then there is a chance of hydrogen bonding. You can see in this case, for fifth case, there are possibilities for hydrogen bonding. In sixth case, there is no hydrogen bonding possible. So fifth one is the stable situation. So the answer will be 1, 4, and 5. 1, 4, and 5. The option B is the correct answer. Now question number 28. Question number 28. The major product formed in the following reaction sequence is. So to solve this question, we should identify the reaction. So TiCl3, zinc copper couple, and a carbonyl group is given. So this is a McMurray coupling reaction. Okay, this reaction is known as McMurray coupling. So it will be like this. MEPH. This is the molecule. McMurray coupling means if you have a molecule like this, ketone, it will react with another molecule of ketone in presence of TiCl3 and ZnC, ZN. Okay, this is known as McMurray coupling. So these oxygen will be eliminated minus O2, and these two carbon will form a new bond. Okay, double bond C. This type of reaction is known as McMurray coupling. Okay, here in this case, we should take the another molecule of this type O. Okay, OMePH. Okay, these two oxygen will remove, and carbon will form a new bond. Okay, so what will be the product you will get? So the product will be like this. So we'll get the product like this. I am writing the first molecule like this, OMe, C, this double bond C, and it comes this hydrogen, double bond OMePH. Okay, this is the molecule we'll get. And now we are treating this one with HCl and H2O. We are treating with acid. Okay, in presence of acid, what happens? This OMe will become OH. Okay, this OMe will become OH. So the product will be like this. Double bond C, pH, OH. It will become OH. Okay, so this also will become OH. This is what happens. This is hydrogen and this is also hydrogen. This is what happens. And you can see this OH is a vinylic OH. In presence of acid, it will undergo ketoenol tautomerism. So it will become, okay, it will move like this. Ready? So the product will be like this. pH, double bond O, this carbon, then comes C, double bond C, then comes another carbon, this carbon, and double bond O, pH. So this will be the product. pH, C double bond O. So the answer will be like this. Option C. Option C is the right answer. In the question number 29, it's all about Diels-Alder reaction. The activation barrier is the order. So for that, we should know what is Diels-Alder reaction. So this is a Diels-Alder reaction. In Diels-Alder reaction, this is known as dienophile. This is known as diene. Okay, and diene and dienophile participate in the Diels-Alder reaction. Okay, in presence of heat. So the condition is we should know the HOMO of diene and LUMO of dienophile participates in the Diels-Alder reaction. That means the electron is flowing from diene to dienophile. That is how electron flows. So if you have an electron donating group on the diene and the electron withdrawing group on the dienophile, that is the best condition for Diels-Alder reaction. So that is what is asked here. You can see it here. In the first case, this is there is no substitution on the cyclopentane ring. Here there is oxygen, there is nitrogen and sulfur. Okay, if you have no substitution, then that diene can participate very easily. In oxygen and nitrogen and sulfur are electron withdrawing group, so that will pull the electron. So it cannot directly participate. So the reactivity order will be like this. First one will have high reactivity, then comes oxygen, 2, then comes nitrogen, 4, and then comes sulfur. So this will be the reactivity order. Okay. So the activation barrier will be in the just opposite to this one. The activation barrier is this is the reactivity order I gave. So the activation barrier will be in just reverse order because the activity will be inversely proportional to activation barrier. Okay. So the answer will be 3, 4, 2, 1. Option C is the right answer. This is also a question from organic chemistry. So I told you, so to see this, by seeing this particular reactions, you should identify which type of reaction is this. And this particular reaction is iodolactonization. This is known as iodolactonization. So cyclohexane is given. So I am writing the cyclohexane in the chair form. Okay, if cyclohexane is given, better you should try like this. OH. Okay, and this is the cyclohexane chair form. First, we should try treat with iodine. So this I let's draw like this. So it will be like this. Iodonium ion is the first species forms. This is the iodonium ion, OH. Okay. Next step, what happened? There is a base given in our weak inorganic base that will remove this proton. So, and that will become O minus, and O minus will attack here and it will remove like this. So we will get the product like this. C, O, iodine, and double bond. Oh, this is the product you will get. Okay, you can see this C O, this carbon bond and carbon oxygen bond are cis to each other, and this iodine and this carbon oxygen bond are trans to each other. So this should be cis to each other, means it should be like this. Okay, like this or like this. Okay, option C and D can be eliminated. And the stereochemistry of iodine, you can see the stereochemistry of iodine and the carbon oxygen bond are opposites. So option B is the right answer. Okay. So this is all about question number up to 30 in the JAM 20 question paper. So we'll discuss the remaining 31 to 40 questions in the next video. Okay, bye.